In today's lesson, we're going to see the final example for looking at specific use cases of the confidence intervals. And in particular, today's example is going to be different than the other ones that we've seen because we are using a variance instead of the mean, right? So we want to come up with a confidence interval for the variance or the standard deviation from a normal population. And so we'll see how to do that. So in today's lecture, that's really all we're going to be focusing on is how to form confidence intervals for the variance and the standard deviation when we're assuming that the population is normally distributed. This process is going to look quite similar. So the important question that we're going to have to ask is what is going to be the sampling distribution here? And that's not something that we've seen yet. We saw when we were dealing with the normal populations, the mean follows a normal distribution itself. But we've not yet considered what the distribution of the sample variance is, right? And so sort of that's an intriguing question to ask. We can take it as fact for this course that if you were to take this statistic written here, which is n-1 times by s squared divided by sigma squared, this is going to follow a chi-squared n-1 distribution. So if you remember from when we were looking at the gamma distribution, the gamma distribution has the specific realization of a chi-square distribution where we're defining the degrees of freedom. And it turns out that the sample variance from a normal population is going to be related to this chi-squared distribution. Now, it's not distributed as a chi-squared directly itself, but if you scale it by the correct values, and so you take n-1 and you multiply that through by s squared, and then you divide by the true variance, then you get that it's a chi-square distribution. Okay. The reason that we were looking at the gamma family distributions was because the exponential is from the gamma family as well as the chi-squared, and this is really sort of one of the main points that the chi-square distribution comes up with in statistics. So we can use the exact same procedures as before, except now we're thinking about using chi-square critical values, right? So we can use the critical values of alpha over 2 and 1 minus alpha over 2 from the chi-square n-1 distribution to form the interval. And doing this gives us this interval here, where we have n-1 s squared divided by the first critical value, n-1 s squared divided by the second critical value. And again, I'll just point out, how did we do that? Well, we're saying that if you take n-1 s squared divided by sigma squared, this is going to follow a chi-squared n-1 distribution. So let's say that we take A is going to be the critical value of alpha over 2 from the chi-squared n-1, and B is going to be the critical value for the chi-squared 1 minus alpha over 2 n-1. And if we just define this statistic here, we just take that to be t, then the probability that A is less than or equal to t, which is less than or equal to B, is going to equal 1 minus alpha, right? And so we have this probability here, which is always our starting point. And then the idea is that we invert this, right? And so if we say A less than or equal to n-1 s squared over sigma squared, right? We want to solve for sigma squared in this case. And so we can multiply both sides and then divide by A, and we get sigma squared has to be less than or equal to n-1 s squared over A, which is exactly sort of the results that we're getting here. Okay? You can do the same thing for the other side of the interval as well. The chi-squared distribution is asymmetric, and so the endpoints here are not going to be equidistant from s squared, right? So we've always seen this as sort of plus or minus the same value. That's not going to be the case with the variance in general. We are still assuming that we have a normally distributed population, okay? And so because of that, because we're still assuming that we have this normally distributed population, this only works if you can test that your population looks to be approximately normally distributed. Otherwise, the variance is going to take on other distributions. If we want to find an interval for the standard deviation instead, we can simply take the square roots of the endpoints here. This isn't going to be perfect. It's not actually going to come from the direct sampling distribution, but it's going to turn out that doing this transformation provides us with a pretty good sense of it, right? And so if you have a confidence interval for the variance, you can use that to find a confidence interval for the standard deviation through the square root transform. Like I said, that's not going to be an exact confidence interval, but it's going to be close enough for most purposes. So, sample variance from a normal population has a chi-square distribution. The degrees of freedom are given by the sample size -1. And if we invert that sampling distribution in the way that we were used to doing, then we can get confidence intervals for the variance and for the standard deviation. And so those are all the specific examples of confidence intervals that I wanted to show. I hope that I've been able to emphasize the point that we're doing basically the same thing. We're starting from that probability statement, and then we're sort of inverting that to get to these confidence intervals that we care about. And so I'd advise you sort of revisit that, but in particular, revisit the general procedure and make sure that that all makes a lot of sense. In the next videos, we're going to start looking at hypothesis testing and other sort of fun procedures that are related to these confidence intervals. So I hope to see you all there.